Hi, everyone, and welcome to this session, Introduction to TFHE and Some Applications. My name is Helena Barmer, and I will be the host of this session. Today with me, I have Nicolas, Gama, Mariya, Gergeva, and I will soon introduce them a little bit more. Just want to briefly mention, if you have any questions for them today, for the speakers, please ask this in the Q&A box. And if you have a general question, you can ask it in the Zoom chat. I will be there to help you and take care of everything as well. So Mariya Gergeva is a director of security innovation at Infer. Her research focuses on lattice-based reduction algorithms and crypto analysis, software security, privacy preserving computations and applications. She is one of the creators of the Tfh Library and Chimera framework. Nicolas Gama is a chief scientist at Infer and also an associate professor at University of Versailles. His research focuses on lattice-based cryptography and efficient privacy-preserving computations. He's one of the creators as well for the TFHE Homomorphic Encryption Library. Very exciting. So happy to have you with us today, Nicolas and Mariya. Nicolas, please welcome to start.
Thank you very much for the presentation. So hi, I'm Nicolas. So I'll talk today about a library called TFHE, which solves something which we call secret computing. So what are secret computing use cases? So there are lots of use cases, both in medicine, especially for finding a cure against various diseases. We have to do some machine learning over genomic data, for example. And one of the problems is that single hospitals never have enough data to do that kind of analysis. More generally, there are other machine learning problems in finance and everywhere where we need to train model and we need to combine data sets that belong to different owners. We can also tackle use cases in physics and astronautics, but they all have something in common. So every time we cannot run the computation just in plain text because the plain text cannot be gathered at a single place. So the primary goal of secret computing is to run an arbitrary function over secret or private data on a public environment. So in other words, this is what we call privacy preserving computation. So as you know, there are lots of privacy preserving computation techniques around here. Anonymization, differential privacy are maybe the weakest one. Then we have federated learning, fully homomorphic encryption, multi-party computation, etc., etc. So in this talk, we'll focus on one library that achieves fully homomorphic encryption, and that's we help developing at Infer. So what is homomorphic encryption? The mathematical definition is a system whose decryption function is homomorphic. So essentially what it allows to do, when you look at traditional cryptography, when we encrypt something and send it from point A to point B, traditional cryptography says that the only thing that we can do while the data is moving is just transfer it. We cannot decrypt it, we cannot see information, and we cannot modify it. Here with homomorphic encryption, the goal is different. We want to allow to do any arbitrary computation on the ciphertext and be able to, at the end of the pipeline, to decrypt the results, but in the middle remain secure against any honest but curious adversary. So here it's really homomorphic encryption in the large sense. We are not able to do just sum and product, but any broader kind of function. So homomorphic encryption. Now homomorphic encryption has become a large consortium that regroups many industries, and that is in the process of standardization. So there are regular meetings, once or two per year, and few white papers, especially on security, application, standards, and skills. And there are also a lot of libraries available. Most of them are open source. And here the focus is on one particular library that is TFHE that we created, and which is one of the first library that was published under the Apache license back in 2016. So let's go back to the origins of TFHE. So at the beginning, there were lattice problems, sphere packings and lattices. They were studied a lot by mathematicians during the 19th century. And when computers arise, there were two lattice problems that were the shortest and the closest vector problem that were NP-hard problems. So what are these problems? Basically, you describe a lattice by a basis. So let's take, for example, the black vectors, and any integer combination of this vector will give you all the green points. And the problem you want to solve, for example, is which of the green point is the smallest? Or, so that's one possibility. Or another possibility is I give you a point anywhere in the space, and you want to solve which one of the green point is the closest to the point I gave you. So of course, in 2 dimensions, it looks very easy because you can draw the green points. But where things get interesting is when the dimension grows. So here in 3D, but yeah, let's go to dimension 100, 200, 1000. And here, the problem becomes really hard because there is no way you can draw the green points. There are far too many. Yeah? But the thing that was very interesting with this problem is not only they were NP-hard, but their approximations were also NP-hard. So if I give you a description of a lattice, and I ask you not to find the exact shortest vector, but just one vector that is relatively short, so any of the red points, in high dimension, it's impossible. In the closest vector setting, it's the same. If I take a lattice and I give you a point that is very, very close to the lattice, so one in the red area, you will still not be able to compute what is the closest vector of the lattice. So this setting is very interesting because it is the problem on which every lattice-based crypto and every homomorphic encryption scheme nowadays are based on. And if you look at this problem, it's something really strange because you are on the continuous space, modulo something that is discrete, and you have to find some approximation problem. So let's take a step back. How can we represent this problem? It's a geometric problem that is multiperiodic. Can you name one compact continuous structure, mathematical structure that is that has n-dimensional periods? There is one structure that does that. It's the torus. This one is a 2-dimensional torus. It has one period, the red one and the pink one. And if you take n-dimensional torus, well, the hard problem on which all the crypto is based, learning with error problem, can be described very simply here on the torus. It just approximates, solve a linear system on the n-dimensional torus and just find an approximate solution. And this is the very hard problem on which the crypto is based. Now, I give you one question. Is it easy to work with a torus? Well, maybe for a human, it's a bit hard at the beginning because we are not used to work on continuous modulus. It's not a ring, we don't have multiplication, it's very strange. So many people, when they have a torus, want to rescale it and take it modulo Q, and actually no matter what kind of Q. And actually the LWE problem was described at the beginning using both modulo Q and the torus. But now, when we come to implementation, like in C, how can we represent the torus? Well, it turns out to be very easy, because just using native int32, for example, is a good approximation of the torus. So when we look at this type int32, usually we believe that it's an int, but there are some annoying overflows. Here, the overflow is something that we need. It's something that maps the geometry of the torus. And on it, we can do native addition, native subtraction, external product with integer. And since the torus is centered on 0, we can even compute distances using the absolute value. But I have something better than in C. If I go down to the assembly, it gets even simpler. It's just one SEMD registered, like ZMM0, for example. So out of all the mathematical structures that exist on the universe, there are not many of them that are represented only by one symbol in assembly. So from a machine point of view, working on the torus is very natural. So in TFHE, if you want to work on torus, the answer is simple. Use TFHE, torus FHE. And it is the shortest link that you will find between hard lattice-based cryptography problem and your hardware. So the TFHE library, you have the link on GitHub, tfhe.github.io. So it's a library with multiple interfaces. So we have one simple API, which represents Boolean operation, and that is fully homomorphic in the sense of geometry. And we have an advanced API that contains more computational models, like SEMD additions, rotations, or even deterministic automata model, or chain of lookup tables. So here in this tutorial, I will demonstrate one usage of the simple API and one usage of the advanced API. So let's start with the simple API. So the goal of this API is if you are able to draw a Boolean circuit, then you can evaluate it in TFHE. So what is a Boolean circuit? It's a graph with different gates. So you have AND gates, OR gates, NOT gates. And when you plug in inputs to a Boolean circuit, like here, you just evaluate each gate one by one. So if you take AND gate, for example, 1 and 1 is 1, 0 or 1, this one is the OR gate is 1, etc., etc. And you get your outputs that are here. So the goal of TFHE evaluation of a Boolean circuit is to do exactly the same as a plaintext evaluation, except that all the bits as input and the output of every gate are encrypted. And that's all we need to know to be able to use the bootstrapping, the gate bootstrapping simple API. So since it is an encryption library, you have a function to generate keys. You have a function to encrypt and decrypt bits. And you have a function to homomorphically evaluate any gate that you want, constant, AND, OR, XOR, NOT, LUX, etc., etc. And of course, the library provides everything you need to serialize and deserialize your ciphertext. So let's take a very simple example based on a problem described in 1982 by Yao, which is Yao Millionaire's problem. And I will depict the problem very nicely here. So we have Snow White and Cinderella. They both have shoes. Each shoe has a price, but of course, you should never disclose the price of a shoe. It's a very sensitive matter. But of course, the two princes may still want to know which shoe is more expensive, X or Y. Yeah. So how can they do that? Well, in 1982, when Yao described the problem, so I think it was not about the price of shoes, it was more about salary. But the solution he gave was a technology called Garbled circuits. Here we'll present a very nice way of solving the technology using TFHE. Yeah. So first, if we want to use TFHE, we'll have to generate keys and parameters to be able to encrypt. So we choose a security parameter. 128 bits is usually enough for crypto. And we'll generate keys. So for FHE, we have a secret key that is used to encrypt and decrypt ciphertext. And we have a cloud key, which is more or less an equivalent of a public key that allows to carry operation over ciphertext. So secret key and cloud key can both be generated in one line with the library. Then once you have the key, you will encrypt your plaintext. So you can view the plaintext as the different price of the shoes on both sides, and you take the bits of this price. So this is a plaintext bit, and you encrypt each bit to form LWE ciphertext. Now, you need to compare the two prices. So in order to compare that, we'll need a comparison circuit. So comparison circuit is a very simple circuit. It's even simpler than the addition circuit. So you have a recursive description of the comparison circuit. So if you have already compared the least significant part of your number, AI and BI, so let's say RI is the result of the comparison between these two, then the global comparison consists in just taking the most significant bit. If they are different, you get immediately the result of the comparison. And if they are equal, you return the carry. So this corresponds to a very simple circuit. You get a XOR gate and a NUX gate, which compares one bit. And to assemble the full circuit, so you need to iterate this circuit and repeat it n times. So here you see that since you have a carry that goes from the beginning of the circuit to the end of the circuit, you get a depth that is linear in the number of bits. And for the TFH library, depth is not a problem. So you will just be able to map the naive circuits and get the results quick enough. So mapping the circuit is very easy. So here we have this comparator that has two gates. So you get, you write your compare function where you put the XOR gate and the NUX gate. And then you have the full circuit that has n copies of the comparator. So you take a for loop and you write your comparator. And boom, you can just evaluate your circuit. So here, this video will go through the source code. So you generate your key set, your encryption key, you encrypt your plain text on both sides. And then you send everything to the cloud. On the cloud side, you get the ciphertext, you execute the circuit, so you recognize the comparator here and the for loop for the whole circuit. And here it's just a verify program to test that everything worked well. So you see it's using the library is very easy. Each function that you need is almost a one-liner, and you can compile it with almost no dependencies. Just link it with the library. So here is an example. So the two numbers here that were entered were 42 and 2017. And you can see that the keys are quite short, the ciphertext also. And when you execute the circuit, it takes less than 2 seconds for you to get the results, which is also small. So that's one of the advantages of real fully homomorphic encryption is that the size of the ciphertext is really small. Okay. So when you evaluate gate by gate, like we presented here, so we evaluate each time a binary gate, and we have a procedure that is bootstrapping that is run every time that allows you to chain any gate that you want in the circuit. The API is very simple. You can evaluate any Boolean circuit, and in particular, if you have a dynamic programming problem, you are able to solve the problem without having to worry about noise propagation or other things. The other nice thing is that, so if you compile it on a CPU, each gate will take approximately 10 milliseconds per core. So of course, if you have multiple cores, you can run multiple gates in parallel. But then something that we should note about this library is that there were many successful attempts to parallelize this library on different hardware. So on GPU, some teams were able to go down to 100 microseconds per gate. And I've heard other dedicated hardware where the time was going even lower. So this was the simple API. Let's look at the advanced API. So TFHE supports many other computational models. So if we look at native operation, we have, for example, additions in parallel and secret shifts, but it also supports other kind of nice models like automata, for example. There are lots of arithmetic operations that you can map to very simple automata. Or we also have very fast evaluation of lookup tables. And here, the example that I will take is the example of computing approximate passwords. So here, what is the setting? So we have cell phones or tablets that gets smaller and smaller, and on this tablet, it gets harder and harder to type a password correctly, because whenever we try to type on a key, we often reach the next key. So the traditional way of storing password on the cloud is to use hash function. So when you compare if a password that I enter is right, you compute the hash of the password and compare it to the hash that is stored in the database. This one match only exact password. It doesn't allow for mistake. Here in FHE, we'll show one use case that allows you to register one master password and accept very small differences as long as the key that was typed is close to the original one. So either because geographically on the keyboard it was a key that was next to the right one, or because you missed a shift or something like that. And this is a problem that we can solve with the advanced mode of TFHE very quickly. So the idea is to, so we have the target password that is encrypted. And for each character that we'll type, we'll sum the distance to the target, and we'll accept the password if the distance is lower than the threshold. So it's a very simple function. Yes, it's quite simple to enter in the TFHE library. So if we analyze that as a circuit, as a multiplicative circuit, it would have multiplicative depth that make it impossible to map on traditional ring-based schemes. But thanks to TFHE that is able to execute lookup table very quickly, you can map this problem as a sum of lookup tables. And here is the demo. So the source code of that is less than 10 lines anyway. So here again, you see that you can generate keys, that every key and every running time are very small. And so here is an example. So let's register a password, like here, Toronto with a big T and 1. So here we have register.bin. The size of the encrypted password on the cloud is 65K. Yeah? And now let's try different logins. So the first login, I will enter the right password. So I have a distance 0, and naturally, it decrypts as accept. Here you can see that the result and the login 256K and 2K, which is already also taken. Here with 2 difference, I got a reject. Here let's try a character that is very close to O on the keyboard. It's an accept. And here on this one, I mistyped the uppercase and I did a second error. So I got reject. 2 errors too much. If I just miss the uppercase, but all the rest is correct, then I have a lower distance. So it decrypts and accepts. So you see that all these examples run very fast. So this demo were executed in real time. They all take less than a second to run. So I'll leave Mariya explain the next part of the talk and give other possible applications of the library.
Okay, thank you, Nicolas. I will just share my screen, but before, if there may be some questions. Okay. Yeah, in the second part of this tutorial, we will show some real applications that are much more applicable in the real world. In our days, the privacy and the security are really important to the future of the digital computing, and the industry as healthcare and financial service are seeing the need for more and more collaboration between the institution and the data sharing. In this context, the privacy is with real high priority in order to meet the different compliance requirements as GDPR or HIPAA. And the interest from life science and the biotech pharma becomes even more important in the context of COVID. Here I just extract some recent study about genotypes, about the genomic studies related with the well understanding of the COVID-19. And we see that it's really important to analyze the genomics to well understand this disease. And of course, the genomic data are really sensitive and we cannot perform them directly on plain text. For that, we will show 2 different applications, both of them proposed as the challenges at the iDash competitions 2018 and 2019. One about the association between the phenotypes and the genotypes, and the second one about secure genotype imputation. Okay, we will start with the first one from I-2018. Here the goal is to test the association between genotypes and phenotypes. This test or this association is really important in order to identify generic variants associated with a disease or a trait. That it's a powerful approach in the understanding of diseases as diabetes, as Parkinson's disease, or even COVID-19. Of course, the data is sensitive. We cannot manipulate all the data in plain text. For that, in this scenario, we will use an genomic server provider in which we will store the data, but in an encrypted way, and we will perform the training directly on the encrypted data using the full homomorphic encryption and in this case, the Tfh library. Okay, to explain the use case, we have study participants, each with the genomic data that encrypted with a public key and send it to the genomic service provider. We have the first part that contains the phenotypes as gender, age, weight. We have an encrypted target that it's related to the disease that we want to learn. And we have also a big data set that contains all the genomic data. Now, the analyst wants to initialize a study, wants to understand to learn which feature or which part of this big data set can be relevant for the to improve the first model, to improve the model based on phenotypes. That means we perform some kind of feature selection. We compute a statistic which features are more relevant for this model and for this disease. And at the end, the output is returned in an encrypted way to the analyst that can decrypt it and use it for the analysis. Now, if you want to modelize that in a mathematical way, we have an input matrix X that it's the phenotypes information. We have the binary vector Y and the big matrix with the genomic information. And at the end, we obtain a vector with the statistic or which feature it's more relevant. The algorithm in plain text to perform this training or this study looks complex, but the important part to note is that it's composed by a first part that it's a logistic regression, and the second part that is a big matrix computations. That means we have this logistic regression with a different number of iterations that it's a dynamic, and to be able to perform an arbitrary circuit, as Nicolas explained, we need the properties of bootstrapping, and that means we need really efficient bootstrapping in order to be sure that our model will converge. For the second part that it's composed by a big matrix multiplication, the best solution is to use a library that performs efficiently fully packed CMD operations. For that, there are two strategies to solve this problem. The first strategy is to use the leveled homomorphic encryption. That means to construct a fixed or static circuit with small parameters and to execute the evaluation on this fixed circuit, for example, with up to 3 logistic regression iterations and with 3 phenotypes. The second strategy can perform or evaluate an arbitrary number of logistic iterations, but for that we need the bootstrapping. It's the full homomorphic encryption strategy. In our solution, we combined the two schemes. The one that Nicolas explained in the first part, the TFHE, that perform the full homomorphic mode that applies the bootstrapping for the logistic regression. And the second part, the linear algebra computation, we used the CKKS scheme that it's really efficient for big matrix multiplications in a parallel or CMD way. For the different strategy, we have performs different benchmarks for 245 patients and 3 phenotypes and around 10,000 genotypes. For the strategy one in the solutions proposed by University of San Diego, based fully on the CKKS scheme, we have the full evaluation of the program of the learning around 3 minutes. In the second strategy, with the TFHE, we have 3 hours, but we give the possibility to run 20 logistic regression iterations and to be sure that the model we will converge. Of course, both are completely parallelizable with multi-thread. In the case of TFHE with 96 core, we have 10 minutes of running time of the training. That means with the both strategy for a program for the training, we are in the order of few minutes. Okay, that's for the first applications, it's the training. Now I will show on a second application that this time is the prediction. It's not the training will be performed in plain text, but the prediction will be performed in encrypted way. In the second case, we have a server that owns a database that contains different DNA information and that can train the model on this data. After that, we have a client that owns an incomplete DNA sequence and that wants to predict the missing pieces on the DNA, but using the genotype imputation server, of course, without revealing the data. What's the scenario? To resume, we have our client with incomplete genotypes with information that it's missing in some of the positions. The client encrypts the data with a public key, send it to the genomic imputation server that perform the imputation, but working just on the encrypted information and send the output to the client that can decrypt it using the secret key. Of course, at the end, the client obtained the full information about the DNA sequence. How we can modelize the data set? The data set is split into parts. We have several individuals. The first part is used for the training, around 1,500 individuals, and for the evaluation we use 1,000. After that, we have the information that it's known, that it's the tag SNP, around 16,000, and the one that it's missing in orange, that it's the target information, and we test with 3 different sets, 20,000, 40,000, and 80,000. Of course, the missing information, it's not just at the end, but it's in the random positions in the database. Now, here in this use case, the important part is that the training is performed on plain text. We use the logistic regression for the training, and the classification or the prediction is performed on ciphertext. The training is a logistic regression based on a few near tag 5, 10, 20. It's the tag that are more related to the target SNP. That means we used just the nearest neighbors. At the end, we obtain a model coefficients in plain text that are used for the prediction. The prediction here, it's linear. It's just a multiplication between the encrypted tag data I that we used, that we encrypt with TFHE, and we multiply with the plain text model M. The algorithm here, it's presented here. It seems complex, but again, it's a sample. It's just matrix multiplication with some packing optimizations inside. Now we execute a few benchmark for 1,000 clients and with different number of targets. But for all of them, we can observe that the full running time that contains encryption, evaluation, and decryption is less than 5 seconds. Even for the data set that contains 80,000 targets. That means we can perform around 18 million prediction per second. This benchmark is given for 16 core, but we can see different runnings with 1, 2, 4, 8 to 24 cores. And with 24, the speed up it's around 10 regarding 1 core. Now, what about the accuracy of the model? We compare the accuracy of our model with the accuracy of the one obtained using a plain text approach. And we can see that both are really close to 1. In our case, if I remember well, we have 0.997. We compare different plain text approach for this imputation problem, minimac, input to BIGO, that give different running times. Of course, this one, it's the one that gives the more accurate model. And we compare with our solutions that it's a linear regression, secure linear regression using the TFHE with that accuracy that it's good and with a running time that it's really competitive regarding the plain text algorithms. And this solution was won the first place at TfhS in 2019. Now to resume, what about the technology versus real applications of the fully homomorphic encryption? With the last example, we saw that circuits was one depth homomorphic encryption are now really efficient, and we can run around 18 million predictions per second. With the first example application, it's also a real application that the computation, it's much more complex, it's a training. And even for the training, we obtain a computation, an evaluation of the homomorphic algorithm in orders of a few minutes. Now I will cite the people from the homomorphic encryption standardization group, in which we try to answer the question if the homomorphic encryption is real world ready, and the answer was yes, we believe it is. Thank you very much, and if you have questions and if you want to join TFhE, we have some open positions, and especially one for federated learning intern. We can write us and we will give more information. Thank you.
Thank you so much, Mariya, and also Nicolas for your presentations. I have made sure to pasted all the links in the chat. So if you want to get in touch with Mariya or Nicolas, you have their emails, and you also have that info.io career. So make sure to apply if you have any background. And for any questions, feel free to ask them in the Q&A box. If you can't find the Q&A box, just paste it in the Zoom chat, and Nicolas and Mariya are here and happy to answer your questions. But I actually have a question for you, that I'm curious to know about. So I want to know, what do you see, so the future for homomorphic encryption and this library? What is the future, and what applications are you hoping to just see built, or anything else that can be upcoming in this field? Would you like to share that? I would be so curious to know. Mariya, would you like to start?
Yes. Yeah, my vision first for our library TFHE, it's to go in the direction to combine the different schemes, and to have the one that Nicolas just briefly recall in the beginning, Chimera framework that combined TFHE with CKKS and BFV. That means different protocols in the same library, that will give the opportunity to run computations with that are approximative, that are on Boolean, that are on big integers, and that will allow really a big field of different use cases inside.
So it sounds like it's an excited future for this, for TFHE, and and your vision for it as well. Nicolas, do you have anything to add there? You're muted, so you have to turn on your microphone.
Yeah, so with retrospect, I think FHE is a very interesting technology. And if we look back at what happened 30 years ago when public key cryptography was invented, no one believed it at the beginning. Everyone said, no, it's too slow, it will never work. And now if you look at what happens nowadays, every single query that we do on internet is encrypted using a public key handshake. So I think the same is going to happen with privacy-preserving techniques, especially homomorphic encryption, that tend to go faster and faster every year.
So this was something you also shared in your slide, Mariya, about like, can this be used now? So like you also mentioned, Nicolas, that people are still a little bit unsure, or maybe still thinking that it's not being able, you can't use it for real or in industry, but you have actually shown that it's a full, you can do it. And if anyone has any questions, they can reach out to you. So now they either just through info, they can find your information there as well, your emails. And I have also pasted it in the Slack Zoom chat. Sorry, not Slack. We're not in Slack now. But anyone else who have a question, feel free to ask it. We have a few more minutes left. So what is the next step for you now with TFHE? What are you going? What's this next step you're heading towards? Would you like to go ahead, Nicolas?
Yeah, so probably the next step is to try to make the FHE engine more robust, more faster, but also to mix it probably with other technologies. So probably FHE is not the only privacy-preserving technique that can be used to solve problems, and mixing FHE with other technologies is also a nice source for secret computing in general.
Anything you would like to add, Mariya, or was that, maybe that was all?
Yeah, I completely agree with Nicolas. We should not look just in one technology, but combine all of them together to obtain something that is really efficient and robust and accurate. I think that that's the future.
So really exciting. And just you said also you're looking for someone to intern that has a background for federated learning. Would you like to just tell a little bit more about that, if anyone is listening now or in the recording, and they can reach out to you?
Yes, of course. Yeah, it's related with the last question. In Infer, we mixed different technology as multi-party computation, fully homomorphic encryption, and also federated learning. That's why now we start to work and to build our federated learning solution. And I think it's a good time for an intern to join us and to work with us on this topic.
What kind of background are you looking for someone who wants to apply as a federated learning intern?
Oh, somebody that that have an expertise or knowledge of machine learning algorithms on different privacy preserving computation, but yeah, especially on the machine learning. I think now it's more important to well understand the algorithms and how they converge, how we can apply them, and after that apply the different privacy preserving techniques on that.
Thank you so much. And anyone else, if you have more questions, just reach out to Nicolas and Mariya through their emails. And make sure if you looking for an internship and you have this background, this sounds really exciting, and just make sure to apply. So thank you so much, Nicolas. Thank you so much, Mariya, for a really nice tutorial and to just tell us more about this exciting TFHE. Looking forward to hear more about the vision and future in the upcoming, maybe in an upcoming session as well. Have a really good Sunday, and everyone who joined in, have a good day, and see you all, I hope, in OpenMined Slack or somewhere out in the privacy preserving communities. Thank you so much.
Thank you very much for the invitation and for the super organization of the event.
Thank you. Have a good day. Bye, everyone.
Bye-bye.